Alright, welcome back, future AP Chem students. This is the second part of the first set of problems, and this is a new concept that we're going to go over. It's called significant figures. Now, significant figures are a measurement that consists of all known digits with a certain amount of certainty. What that means is, in science, when we take a measurement of something, we only accept the numbers that lead to the greatest precision and greatest accuracy. Those numbers are called significant figures. And it's not very difficult to figure out how many significant figures are in each number. You just need to follow these 5 basic rules right here. And the first rule is, all non-zero numbers are significant. Okay? So if you are a non-zero number, you are significant 100%. That means 1, 2, 3, 4, etc. Rule number 2, that's up next. Trapped zeros are significant. That is 101, 40.07, and 1003. If you see these examples right here, these zeros right here are trapped between non-zero numbers. And if you ever come across a number like that in your measurements when you're collecting data, just know that those zeros are significant. We have to consider them appropriate and valid in our measurements. Rule number 3, here's our first non-significant example. Leading zeros are not significant. Okay, leading zeros are not significant. If you lead a number, you are not significant in any case. And I know it seems a little counterintuitive because in front usually means the highest position. But in the case of numberland and precision and accuracy, if leading zeros are not significant. So in these cases right here, I have underlined these zeros to represent that they are not significant. This number, 0.015, only has 2 significant figures in it. Okay? 2 significant figures from these 2 non-zero numbers right here. These 2 zeros don't count. This number right here, this is the number 1. It was just put with 2 leading zeros in front of it. Mathematically, that's not incorrect. You're more than welcome to put as many leading zeros in front of a number as you want to, as long as there's not a decimal here to change that number's value. So this number 1 right here has 2 leading zeros which are not significant. So there's only 1 significant figure in this number right here, and that's that non-zero 1 right there. This number, 0.111, only has 3 significant figures in it because this leading zero right here, is not significant. Okay? Only these non-zero numbers are significant right here. Let me jump back up to the second example. There are 3 significant figures in this number. Okay? The 2 non-zeros plus the trapped zero right here, making it 3 total significant figures. This one also has 3 significant figures. The 2 non-zeros and the trapped zero between the decimal and the 4 right here. Okay? This number, 1003, has 4 significant figures. Okay? The 2 trapped zeros right here are significant, plus the 2 outer non-zero numbers. Let's move down now to example number 4. Trailing zeros are only significant if there is a decimal point. If you don't know what a trailing zero is, it's basically zeros that come at the end of a number. Alright? And I have underlined in red cases where they're not significant, but let me go over this in general. This number right here, 1.0010. This is a trailing zero right here. It comes at the end of the number. This zero is significant. It is valid in our measurement because there is a decimal right here. So total number of significant figures in this number, 1, 2, 3, 4, 5 significant figures. The 2 trapped zeros are significant. The 2 non-zero numbers are significant. And the trailing zero is significant because there is a decimal. Let's move on to the number 1200.00. These 2 zeros are trailing, and so are these 2 zeros here. There is a decimal point here. Therefore, these trailing zeros are significant in our measurement. They are valid and lead to the greatest amount of precision and accuracy. We have 1, 2, 3, 4, 5, 6 total significant figures in this number because there are 2 non-zero numbers and then 4 trailing zeros with a decimal. 2400. Here's an example of a number that does not have the amount of significant figures we would expect given these trailing zeros right here. These zeros are trailing, but there is no decimal here, okay? So therefore, these numbers are not significant, these two zeros. There are only two significant figures in this number because there's not a decimal place. The number is still 2,400. We just do not consider these last two numbers to be significant, meaning that whatever measurement or data came about to give this number, it's probably not the most accurate. Okay, something that the scientists could have done to probably make this number a little bit more accurate. The fifth rule: exact numbers such as conversion factors, defined numbers, or counted numbers have an infinite number of significant figs, or sig figs as we say for short. We will see this more in action when you go to doing math with significant figures. Things that involve, stoichiometry, mole conversions, or dimensional analysis will take this rule more into account. So let's go ahead and go over a few math examples that involve significant figures and how we can get the appropriate number of significant figures from them. Let's take a look at our first example right here. Let's do significant figure calculations with adding and subtracting. Let's take this first example here. 1.011 plus 2.03. You can easily plug this into your calculator, but how many significant figures are you allowed to have in this number? Well, you're only allowed to have the total number of significant figures as the least number of decimal places when you're adding and subtracting. What does that look like? Mr. C, what did you just say there? Well, the easiest way to figure that out is to line these up linearly and add them this way. So let's do it 1.011 plus 2.03. Remember, when you're adding decimals, take this back to elementary school, you have to line up the decimal places, okay? And now you just go through and add it like you normally would. There's no number here, so you just bring down that one. 1 plus 3 is 4, 0 plus 0 is 0, there's my decimal place, 1 plus 2 is 3. So I have 3.041. I cannot have all those numbers in my final answer. I can only have as many decimal places as the one that has the least number of decimal places after the decimal place, I should say. So the one that has the least amount of decimal places is 2.03. 2 places after the decimal. This number has 1, 2, 3 places after the decimal. So my final answer can only have 2 places after the decimal because the number with the lowest places after the decimal takes priority. So I would have to rewrite my answer as such. 3.04. Okay? I have to kick off this last one and then round this 4 to the nearest hundredth place in this case to 2 places after the decimal because that's the amount I'm allowed. So total in this problem, I'm only allowed 3 sig figs, or 3 significant figures. Let's do another example, the subtraction example. 13.0 minus 4.100. Now, when you're subtracting decimals, you've got to be careful, especially when you're dealing with significant figures. You can't just bring down these zeros willy-nilly like there's no problem. You actually have to subtract them properly. Okay? So we're going to add some imaginary zeros after this 13.00 so that we can properly subtract this number. Just keep in mind that those zeros are imaginary and that they're not really there, and that 13 only has 1 place after the decimal, while the 4.100 has 3 places after the decimal. So now, 0 minus 0 is 0. 0 minus 0 is 0. 0 minus 1, well, we're going to have to borrow and carry. And then we're going to have to borrow and carry again, or just realize that 12 minus 8, or 12 minus 4 is 8. Okay. The reason why you have to add these imaginary zeros right near is because this number could have been like 1, 2, 3, or 4, and then you would have to keep borrowing and carrying until you got to the appropriate number here. So whenever you have a situation like this and the smallest number has more decimal places than the biggest number, then you need to add the imaginary zeros. Always keep in mind that they're imaginary, they're not there. This number only has one place after the decimal. Okay, that being said, it only had one place after the decimal, so what am I going to call this number then? If you said 8.9, you were correct. Only one place after the decimal is allowed, so this has a total of 2 significant figures. Okay, 2 sig figs. When it comes to figuring out significant figures with math, adding and subtracting is the most difficult. Up next is the multiplication and division, and that's by far the easiest. So let's move on to that example next. Multiplication and division with significant figures. This is super simple, as I said. All you need to do is take the number that has the least amount of significant figures, and that's the total amount that you're allowed. So let me say that in more formal terms. When you're dealing with multiplication and division, you take the number that has the least amount of significant figures, and that's how much needs to be in your answer. Okay? So let's do this first example right here. 5 times 1.005. We'll plug that into my calculator here. Put it up here. 5 times 1.005 comes out to be 5.025. But this number has one significant figure. This number has 1, 2, 3, 4 significant figures. This one has the least amount of significant figures, so I'm only allowed one significant figure in my answer. This number rounded to one significant figure is 5. Alright? Let's move on to the next example. 1015 divided by 26. Division works the same as multiplication when it comes to determining the amount of significant figures. So let's do 1015 times 26. You get 26,390. I am only allowed 2 significant figures in this answer because there's 2 here, 4 here. I have to take the one with the least amount. So I have to round this thing to 2 significant figures. Well, 26,000 rounds to 26,390. Here are the 2 significant figures right here, so I have to round to this place right here with this 3. Okay, that's going to be 26000. No decimal places, nothing like that. All you get is 26,000. Why did I choose it? Why did I choose it for that? For the 26? Well, if I had tried to do it with the 3, I would have ended up with 3 significant figures because this would have been 26,400. I can only have 2, so I need to take it to the thousands place here. This 3 will not round this 6 at all, so it'll just be left with 2600. And these numbers right here, these 3 zeros, are not significant because they're trailing and there is no decimal place. So 2 significant figures only. For the sake of interest of time, I don't have much more. Let's go over an example where Rule 5 goes into action. Now remember, Rule 5 says exact numbers such as conversion factors or defined numbers have an infinity amount of significant figures. So this conversion factor right here, where 1 liter is equal to 1,000 milliliters, this is a conversion factor. We don't take it into account when we're looking at significant figures. This is an example of Rule 5, a definition, or in this case, a conversion factor. We do not count these at all in the significant figures. Here was our original number, 0.124, that has 3 significant figures. That means our answer has to have 3 significant figures. We don't count this. It's not insignificant, we just don't count it. So if you recall from the first example, this is 124 milliliters. 3 significant figures because there's 3 significant figures right here. Alrighty, that's all I have time for, and just in record time, I only have 10 seconds left. We'll see you soon for Set 2. Take care.